In this video, I'm going to talk about RL circuits. R stands for resistor and L stands for inductor. So I have a series circuit with a resistor and an inductor connected in series across a battery. This is resistor, this is inductor. I'm adding a switch as well. I'm going to break the circuit. I'm going to add a switch. Switch is now open. So there is no current flowing through the circuit. If there was no inductor in the circuit, if I remove this inductor and when I close the switch, what would happen? The current would increase to its maximum value immediately, right? Let's say the maximum value of current is 2 amps. So the current would increase from 0 to 2 amps in no time, right? If you draw a graph, time on x-axis and current on y-axis, the moment you open the switch, the current would reach the maximum value in no time, right? So the graph would look something like this. Then it's a steady current flowing through the circuit because battery is the voltage source. Yeah. Okay, so this is Imax. This is the case if there was no inductor in the circuit. But if you add an inductor, the inductor would oppose any change in the current in the circuit. Yeah, switch is open. There is no current flowing through the circuit. Current is 0 amps now. I'm going to close the switch, see what happens. The current starts increasing from 0 to its maximum value, let's say 2 amps. That's an increase, right? So there is an increase in the current flowing through the inductor. So there is a change in the magnetic field produced by the inductor that would create an induced voltage in the opposite direction, Lenz's law, and that would oppose the increase in the current. So now if you draw a graph, time on x-axis, current on y-axis, it won't be a sudden increase, but the current would increase gradually to the maximum value. Yeah, there is a time delay, right? You can see a time delay here. This is 0, this is some value t. There is a time delay here. We're going to talk about this time delay. Okay, a characteristic of RL circuit is called time constant. It is denoted by a Greek letter tau. Tau indicates how quickly the current in the circuit changes with any changes in the voltage in the circuit. Tau is equal to L over R, where L is inductance, R is resistance. Now let's discuss two different cases. Case number 1, we have an RL circuit, resistor, inductor. They're connected to a voltage source, V EMF. This is L, this is R. I'm going to draw a graph. Time on x-axis, current on y-axis. Let's say the time constant of an RL circuit is 0.5 seconds. The graph would look something like this. Yeah, this is for an RL circuit with tau 0.5 seconds. Now I'm going to increase the tau value. I'm going to increase the inductance of the circuit. So the tau would increase, right? Okay, this is for tau value, let's say 5 seconds. Sorry, 1 second. Another RL circuit, this time tau value is let's say 2 seconds. The graph would look like this. So this graph indicates that if you increase the tau value, the circuit would take more time to reach the maximum value or the steady state. Now let's define an equation for this series RL circuit. Yeah, I'm going to use Kirchhoff's loop rule. Current is flowing in this direction. Yeah, I'm going to choose a loop. This is my loop. It's a counterclockwise loop. I'm going to assign the signs. This is minus, this is plus, this is plus minus, current is flowing this way, so plus minus, current is flowing this way again, plus minus. So how do you write the equation for this circuit using Kirchhoff's loop rule? We're going counterclockwise. Minus to plus is an increase, so plus VEMF. Plus to minus is a drop, so minus voltage across the inductor. Plus to minus is a drop again, so minus voltage across the resistor. That's our whole loop. They would add up to 0. And what is voltage across the inductor? VL equals L di over dt. What about the voltage across the resistor? It's IR. Ohm's law, right? V equals IR. So I'm going to replace VL and VR. VEMF minus L di over dt minus IR equals 0. So this is the equation for this circuit. We can take LDI minus LDI by dt and minus IR to the right hand side. VEMF equals LDI by dt minus IR, plus IR. So write that equation one more time. VEMF equals LDI over dt plus IR. The solution for this differential equation is I of t equals VEMF over R 1 minus e to the power of minus t by tau. So what is tau? Tau is L over R, right? I'm going to replace tau with L over R. So I of t equals VEMF over R 1 minus e to the power of minus t over L over R. This is in the form A by B by C. So we can flip it and flip the denominator and multiply A times C by B, right? This is the final equation for current as a function of time. I of t equals VEMF over R times 1 minus e to the power of minus RT over L. This is the final equation for current at any time t when a source of EMF is connected. The same circuit, a battery and an inductor. This time I'm going to disconnect the battery from the circuit. I'm disconnecting the battery. Sorry. Yeah. Okay. So this is our circuit now. This is our complete circuit now. We don't have the voltage source in our loop. This is L. This is R. Initially, let's say the current flowing through the circuit was 2 amps. That's the maximum current, I max. Because there is no voltage source in our circuit now, the current should drop to 0, right? 2 amps to 0 amps. Because we have an inductor in the circuit, this would be a gradual decrease. The equation for current at any time t when the voltage source is removed is VEMF over R. that is the maximum current, I0, maximum current, or Imax, yeah, V EMF over R, times e to the power of minus t by tau. Tau is L over R, so I of t equals V EMF over R, e to the power of minus t over L over R, or I of t equals V EMF over R, e to the power of minus RT over L. Yeah. I'm going to summarize this. Charging, that is when a source of EMF is connected, the equation for current at any time t is V EMF over R, 1 minus e to the power of minus t by tau. If you replace tau with L over R, you'll get I of t equals V EMF over R, 1 minus e to the power of minus RT over L. Yeah. This is for charging when a source of EMF is connected. Now for discharging, when current decreases, the equation for current at any time t is the initial current I0 times e to the power of minus t by tau. Initial current is V EMF over R, and tau equals L over R. So I of t equals V EMF over R, e to the power of minus RT over L. These are the main equations.